Hello, and I hope everybody's having a good start to the week. Today, we're going to be beginning a new unit on waves, and we're going to distinguish between two types of waves. There's a transverse wave, which is the kind of wave you're probably thinking about, and it's the kind of wave you see on the animated GIF above, and a longitudinal wave. And these waves, you're going to see that they're going to have different names, and they're going to have different behaviors. So what you're going to need today is you're going to need a document that I had uploaded to Google Classroom, and it's going to be an introduction to Waves note sheet, and you are going to type in notes as we go along. For some reason you cannot get your notes typed up for lack of access with a device, then you can do it on a blank sheet of paper, and then I'm going to have you upload those photos to the document that is on Google Classroom. So if you have any issues with that, please contact me. All right, let's get started. Okay, so when we're thinking about waves, we should ask ourselves, what is inside of a wave? Well, let's start with the definition. A wave is a repeating disturbance or movement that transfers energy through matter or space. And we've talked about some of these waves previously. We haven't talked about this yet, but ocean waves, they transfer energy through water. Okay, that's obvious. Earthquake waves, they transfer energy through the earth. That's the one we've talked about a lot. And we're going to be talking about some of those waves with different terminology. So light wave is a type of wave that can travel through empty space. That's what makes it possible to send messages from Earth to Mars when we have the Mars rovers, and they can send back these images, or satellites that we have around other planets. We even have a satellite that has left the solar system. It was from something like 1970. We're able to communicate back and forth to that satellite because light has that ability to travel through empty space. And we know, of course, that outside of Earth's atmosphere, outer space, there's no matter there at all. Be sure to pause this video as you need so you can catch up and take whatever notes that are required. Okay, here I've got a nice animation of water dropping into a pool of water, and you see the ripple effect. So just like water falling into the water, if a pebble or if you threw a rock into the water, so you're taking that kinetic energy of that falling rock. Remember that kinetic energy is the energy of movement. And so you're transferring that kinetic energy into the water. Well, it doesn't really stop there because the energy is transferred into the water molecules in the immediate area. And then that transfers kinetic energy into the water molecules right next to it, which transfers energy into the water molecules next to it. And so it just keeps on going. And so we see the ripple effect of this energy being transferred. And these ripples, they're waves. So a common misconception is that waves carry matter and they carry material and they move material from place to place. That is not the case. Waves don't carry the material in the same direction as the waves travel. Now you can see this animation above this, I guess, buoy floating in the ocean. It is going up and down in this circular motion, but it is not going back and forth. Like it's not moving to the left or to the right. it primarily, after each wave passes, it stays in the same area. So only the energy that's transferred by these waves is what is moving forward. Matter is not transferred. So if you were in a boat in the ocean, for example, the boat would go up and down, obviously, as the waves pass, but you're going to stay primarily in the same position. There are things called ocean currents, for example, or a river might be flowing in a certain direction that might push you down, but that's not because of waves. That's because there's movement of the water. And ocean currents are like little rivers that are flowing inside of the ocean, different than waves. Okay, so most people have played with ropes or strings, and you pull it up and you whip it down and you see that wave that just goes down it. It's fun. So you're creating a pulse of energy. Remember, waves transfer energy. You're creating this pulse of energy, and it's going to travel to the end of the rope, and it'll even travel back if all that energy is not used up. So it's going to continue to travel until there's no more energy. Anything that moves up and down or back and forth in a rhythmic way is vibrating, and all waves are essentially vibrations. It could be the vibration of a guitar string, for example, where you'd be transferring the kinetic energy of the guitar string into sound energy. So if we're going to categorize our waves, one type of wave is a mechanical wave. These are the waves that can only transfer energy through a medium. Well, a medium, that's a solid, liquid, or gas matter that waves are traveling through. So not all waves need a medium. If you remember what we had previously discussed about light. So light waves, the entire electromagnetic spectrum, I gave some examples up here like radio waves, microwaves, X-rays, they can all travel through empty space. Any kind of a light wave can travel through empty space. So light waves are not mechanical waves. All right, the first type of wave is a transverse wave. So this is a wave that vibrates at right angles to the direction of its propagation. Sounds a little technical, but it's pretty easy. So basically the matter that the wave is traveling through, if we look at this image right here, you can think of it as the matter going up and down, up and down. So the motion of the wave and the energy of the wave in this example is going to the right. But the vibration of the molecules or the matter is going up and down. So that's what it means by the right angle. So the matter is going up and down while the energy travels to the right. So waves in the ocean move horizontally while the water moves up and down. And so when you're shaking the end of a rope, the transverse waves are made. Energy goes forward, the vibrations are side to side, and that is at 90 degrees to the wave motion. Compressional waves. So on this animation that you see at the bottom, at the top, we have the transverse waves, and at the bottom we have longitudinal waves. And so the transverse wave right? It's this wave that we see right here in the previous slide. Let's go back. So the longitudinal wave is another name for a compressional wave. So longitudinal wave is a compressional wave. We called them previously in the earthquake unit from last semester, we called them P waves or push or pull waves. So that's a lot of different names for one type of wave. So compressional waves are also called longitudinal waves, which are also called P waves. And in our class, we called them push and pull waves. And that's what they do. So by definition, a compressional wave is a wave that matter vibrates back and forth in the same direction that the wave travels. Now remember, the matter is not moving. It's not being pushed forward by the wave. It returns to its same position after that energy has gone past it. So we had seen in my classroom last semester when we had the slinkies out, you could if you compress the slinky by pushing it forward, and then you would see this compression as it goes down, and then it would just stretch right back out. So it does look like the whole spring is moving forward, but it returns to the original position after the wave passes. So remember that waves do not move, they do not transfer matter, they transfer energy. Sound waves. Sound waves are a type of compressional wave. So when sound is made in the air, molecules are squeezed together, just like the coils in the slinky from the previous animation. And so these compressional waves, remember they're also called longitudinal waves. You can see right here, this is where the air is compressed. And then there's this place right here where these particles in the air are further apart than anywhere else. Now it's kind of small here, but that is called a rarefaction. A rarefaction is where it's stretched out, and we can see it right here. And these compressional waves, one wavelength, like one peak to peak, would be from one compression to the next compression. It could also be measured by one rarefaction to another rarefaction. I just personally find it easier to recognize the compressions. And so compressions travel through the air to make the wave, and we eventually hear it because it hits our ear. Well, what does it look like when it comes to our ear? Glad you asked. So this animation demonstrates when those compressions get to your ear, what happens. So right here, where my cursor is, that gray looks like a diamond. It's just a flat surface here. That's your eardrum. And so your eardrum literally moves and vibrates. And if we zoom in on this area beside the eardrum, we have the system of bones. It looks a little bit like a kick drum from like a drum set, where you just step on the pedal and it hits the drum. That's what's going on. And that drum pushes on this, it looks like a snail, on this area that looks like a snail, and it's called the cochlear. And this is what helps generate electrical signals that go to your brain. Now, thing to remember about sound waves can travel through all kinds of materials. Travel through water, it can travel through wood, it can travel through brick, it can travel through just about anything. And so when this happens, the particles in these materials are also pushed together, and they move apart as the waves travel through them. And finally, you can see in this animation, your eardrum vibrates when the sound reaches your ear. Okay, water waves. Water waves, they're not purely transverse waves. They are a combination of transverse and compressional waves. And when there's something floating in the water, like the seagull here, you can see that it has like a little bit of a circular motion as it rides up and down the hills and the valley of the water wave. But in general, it's just chilling, it's staying in place. The wave is actually moving to the right, and whatever is on top of the water is just floating up and down in this circular pattern. Seismic waves, known as earthquake waves, they break the crust of the earth, and that's what creates the seismic waves. They can be compressional waves or transverse waves or a combination of both. Remember in the previous unit, compressional waves are the push and pull waves. We called them P waves. And the transverse waves, we called them then S waves. And remember, those were the two types of earthquake waves that helped us discover that the earth was made of layers. All right, so that ends this lecture. Um, I hope everybody is well. Be well. I will be posting some other things to Google Classroom, some projects that we can work on to hopefully make waves a little bit more fun. Until next week, guys, you be safe and be well. Take care.